Okay, so we've been working in separable differential equations, and we are now going to solve the problem of Newton's law of cooling. So we are going to have an object. It could be a ball. In our case, we're going to use an egg. T is the temperature of the object. T sub S is the temperature of the surrounding of the object. And T naught is the initial temperature of the object. Okay, so we can place an object in water. We need to know the temperature of the object. We need to know the temperature of the water. We need to know its initial temperature. Okay, that is where we're starting, and then T is what we're trying to find. Okay, so we are going to use the fact that the rate of change of temperature of an object is proportional to the difference in temperature to the difference in temperature of an object. The rate of change of the temperature of an object is proportional to the difference in temperature of the object and its surrounding medium. Okay. Okay, so since it's proportional, that means it actually equals it by a constant. So we have dt is equal to k times t minus ts. And it turns out we need it to be negative. The reason why is if the temperature of the object is greater than the temperature of the surrounding medium, this is positive, this is negative, because we're assuming K is positive. So therefore, the rate of change is negative. In other words, the object loses heat. So if it's greater, the temperature of the object is greater than the surrounding, it loses heat. If the temperature of the object is less than the surrounding, it gains heat. So here, K is the diffusivity. And every object has its own diffusivity. That means the rate at which it loses heat. Okay, so we're going to solve this like a separable differential equation. So we're going to take dt and we're going to divide by the t minus ts, and that's going to equal negative k dt. Okay. So now I'll take the natural log and get capital T minus ts on this side is equal to, oh, I'm sorry. I'm integrating. I'm a little discombobulated between my two classes. I just, okay. There we go. Now you know what I'm doing. So now we get the natural log of the absolute value of T minus Ts is equal to negative KT plus a constant. Now remember, we're trying to solve for T, the actual temperature. So we get E to the natural log of the absolute value of T minus Ts is equal to E to the negative KT plus a constant. Now remember from before, we can split this as E to the negative KT times E to the C, and then this E to the C, we let that be its own constant. So we get T, absolute value of T minus Ts is going to equal constant A times E to the negative KT. Okay, now we're going to drop the absolute value because we're going to let the positive or negative of the absolute value appear in the coefficient A. So I'm going to have T minus TS is A e to the negative KT. So now I can solve for T. So T is equal to TS, that's the temperature of the surrounding, plus A e to the negative KT. Now, this is only helpful if I know what the temperature of the object is at the beginning. So we're going to say T of 0, that's the temperature at the initial start of our examination of this object, is T naught, which we called its initial temperature. So therefore, I'm going to plug that in. So this says T at T is equal to TS plus A e to the negative KT. So when I put in 0, I get T0 is equal to TS plus A e to the 0. So we know e to the 0 is 1. So that implies A is equal to T naught minus TS. So now we have a completed formula for temperature of an object. It is equal to TS, the temperature of the surrounding medium, plus the initial temperature minus the temperature of the surrounding medium times e to the negative KT. Here, K is again the diffusivity, it's a positive value, and T is our time. Okay, any questions on the derivation? Basically, it was a separation of variables problem, just like the ones we had done in the past. Okay, I want to solve one problem. I've already solved one in this section, so I'm going to solve this type of separable differential equation. Now that we know the formula, here's our problem. So a hard-boiled egg at 98 degrees is put in a sink of 18-degree wet water. After 5 minutes, the egg's temperature is 38 degrees Celsius. Assuming that the water has not warmed appreciably, how much longer will it take the egg to reach 20 degrees Celsius? So what this is saying is, although the egg is losing temperature, that it's losing heat, it's not warming up the water significantly. Kind of like if you jumped into the ocean, you're going to be losing heat, but you're not warming up the ocean by that much. Okay. All right. So I'm trying to solve for T. Somebody give me some information. What do you see in this problem? What did they give you?
The degrees
Hello?
Celsius.
Rodney, what do you say?
The degrees Celsius of the hard-boiled egg and the temperature of the water.
Okay, so the initial temperature of the hard-boiled egg is 98 degrees. And the temperature of the water or the surrounding medium is 18 degrees. Okay, so that's a great part of our problem. Okay, so we already know that now. So now we know that T of T is 18 plus 98 minus 18 times e to the negative KT, or T at T at any time T is 18 plus 98 minus 18 is 80 e to the negative KT. All right, so now they give me some other information. What do they give me?
Wait, hold on.
What happens after 5 minutes?
Oh, the egg's temperature is 38 degrees Celsius.
Okay, so they give me the egg's temperature, T at 5, has to be 38. So the temperature after 5 minutes is 38. So that means we're going to put a 5 in for T. So little t. So we're going to get 38 is equal to T at 5. But that is 18 plus 80 e to the negative k times 5. Oh, I think the only thing left in there is k. So I get 38 minus 18. So I get 20 is equal to 80 e to the negative 5k. So I can divide and get 1 over 4 is equal to e to the negative 5k. Now I need that 5k out of the exponent. How do I get the 5k out of the exponent?
Natural log.
Natural log. So natural log of 1 over 4 is the natural log of e to the negative 5k. All right, good. So their inverse functions, 1 over 4 is e to the negative, I forgot my natural log. Natural log of 1 over 4 is negative 5k. So therefore k is minus the natural log of 1 over 4 divided by 5. Okay, so what is that? That says k is equal to the negative natural log of 1/4 divided by 5. And there's my k. All right, so now I know what k is. That's what goes in my formula. So here, back where my formula was, I now know what k is. So I can put k in for any time. Okay, so the question is, how much longer will it take the egg to reach 20 degrees Celsius? Okay, so let's find out how long it takes for the egg to reach 20 degrees Celsius. So we need T of some number, we don't know what it is, to be 20 degrees. So we have 20 degrees is equal to 18 plus 80 e to the negative k, we know, times t. Now we got to remember, k is already known. I'm just not trying to put it in there right now, but k is known. So we're solving for t. So we get 1 over 40. Oh, I'm sorry, moving too fast. I get 20, so I get 2 is equal to 80 e to the negative kt. So 1 over 40 is equal to e to the negative kt. All righty, we're going to take that natural logarithm again. Very helpful to us. 1 over 40 is equal to the natural log of e to the negative kt. So now we get the natural log of 1 over 40 is equal to negative k times t. Now remember, k is known. So therefore t, the one we want, is negative natural log of 1 over 40 divided by k. Okay, so let's find out what that is. So where's k? There's k. Okay, so t is equal to negative natural log of 1 over 40 divided by k. And that is equal to 13.3 approximately minutes. So it takes 13.3 minutes to reach 20 degrees. So we've already waited 5 minutes for it to become 38 degrees. So we need to wait an additional 8.5. So we need to wait an additional 13.3 minus 5, which is approximately for us 8.3 minutes. Okay, so that's how much longer we have to wait. Okay, any questions about this problem?
How'd you calculate the approximate value?
Of what?
The natural log of the 1/40.
Oh, this is OneNote. OneNote does the calculation. So here I put in, so you talking about the whole problem? Or just at the end?
Just like at the end.
Okay, so when I got to this point, because we took the natural log of both sides, I knew I needed to solve for t. So if I'm solving for t, I have to divide by k and then put the negative on the other side. So then OneNote actually does this for me, so I don't have to use a calculator. It's easier in class to do it this way. So I just did negative log of 1/40 divided by, and I put in the value that we got for k. And that gave me t. Rodney, does that help?
Yeah, I understand now.
Okay, so in the other class, the student said, well, Dr. Lott, how are we going to do this if we're on the test? Because we don't have calculators. So let me show you how to do this if you were on a test. So if you were on a test and I gave you this problem, you would do exactly what we did, but when you got down to k here, you would leave k just like it is. So at this stage, here's your k. So now that you know k and you carry k through, when we get down to the end, so on an exam, you would have t is equal to negative natural log of 1/40 divided by k, where k is equal to the negative natural log of 1/4 divided by 5. So on an exam, you would have t would equal 5, because I'm going to divide that. So I'm going to get 5 times the natural log of 1/40 divided by the natural log of 1/4. And so the answer to the problem would be that number minus 5. Okay, any questions?
So we only have 2 exams left to take?
Yeah, I guess so. One of them's next week.
Will there be
Yeah.
a final?
You have a final? Absolutely.
So it's 3.
We've taken 3 exams.
I'm saying we have like 3 exams
Oh, yeah,
left.
yeah. 3 more major. Okay, yes, if you count the final, yes, you do have 3 more major exams.
Oh, okay.
Okay, any questions? That's it for separable differential equations.